Welcome back to part 3 of lesson 15. This is the final part. Today, we're going to conclude this lecture by talking about the fundamental theorem of linear programming, which states the following. It says, if you have a polyhedron with at least one extreme point, then either the LP is unbounded or it attains its optimal value at some extreme point of the polyhedron. For the purposes of this, the intuitive proof or the intuitive ideas of the proof we're going to present to you, because we're not presenting all the full details, we're just going to try to sketch out what the proof is like. We are going to assume we're maximizing. Okay, so we're assuming we're maximizing. And you should keep in mind the theorem works if we were minimizing too. Okay. All right, so let's start this proof. So make sure you understand the statement. Hit pause here and ruminate about what this means. The significance here is this theorem, so the FTLP, as I will refer to it sometimes, means our simplex method, the main algorithm we are coming up with, is going to work. So it's a really important theorem, which of course you should have guessed from the title, fundamental theorem. Okay, so let's just assume, so what do we need to do? We need to show that an optimal solution is going to exist at an extreme point. So the first thing you might say is, well, what if we were not an extreme point and say this point X, and could it possibly be the max? So let's just think about what that would mean. If X had no improving directions, well, all the directions, what does that mean? So I'll put a question mark there to indicate what does that mean. Well, all directions are feasible here. You can see that from the picture itself, right? Because any direction from here, right, that circle encloses all the directions. They're all in the feasible region, so they're all feasible directions. Okay. If there's no improving directions, then what? Well, that means that C transpose D is less than or equal to 0 for any D, right? So anything pointing in any direction here has to have that. So if C transpose D now is strictly less than 0, what does that mean? So let's suppose it were in this direction here. So this direction D had C transpose D less than 0. Well, what direction is this? This direction, and the exact opposite is minus D. And then C transpose minus D equals minus C transpose D is positive, which means we do have an improving direction, which would contradict. That's a contradiction. Okay, so then, right, because we said there's no improving directions. Then C transpose D must equal 0 for all D. So in particular, I can move towards this boundary. And this point here, let's call it Y. Well, because C transpose D equals 0, that means that C transpose Y, which is going to equal And let's call this direction here, which has C transpose D equal to 0. Let's call it D prime. There's some step size, so that y equals x plus lambda d prime. And C transpose y equals, C transpose x plus lambda d prime, which equals C transpose d plus lambda C transpose x plus C transpose lambda d, and of course this equals 0. So this just equals C transpose x. Okay, so we're on the boundary now, and we have the same value as that x. Okay, so if it were here in this middle of the boundary, and again we have to think about y. Maybe y, there is a way to improve, maybe there's not. We got there because there wasn't a way to improve. But now let's just suppose we're at the boundary again. So this is sort of a new idea. If there's no way to improve still, okay, so if there's a way to improve, we know that you're either going to improve and continue improving as much as you can to the other boundary, or maybe you improve all the way down here to an extreme point. Anyway, we're going to keep repeating this idea, and we're going to keep moving towards more and more boundaries. So we keep repeating the idea of using directions towards more and more active constraints. That's what the proof does. And you can see that you're always going to have these directions. Either if you claim that you can't improve anymore, then you're always going to be able to come up with directions that don't hurt you, that keep you at 0. And eventually, if you keep repeating that enough, you're going to arrive at an extreme point that's optimal, because there's no more ways to improve and you're already at extreme point. And you're at an extreme point. Note that if you're here and there's no improving directions, as we assumed about that original point x, it means that this whole boundary is optimal. Now, I understand this might be a little confusing because you might be thinking, but doesn't this mean this whole space is optimal? And that's true for this small two-dimensional case, but the proof, of course, needs to work for n dimensions. And in that case, once you get into higher and higher dimensions, you don't get to assume the whole space is. The technical aspects of that refer to the fact that you're in some subspace of the polyhedron. If that didn't really make sense to you, don't worry too much about it. I can make that clearer for you if you want. That's a bit out of the scope of this particular course. Something that you would discuss if you took a graduate course in linear programming. Anyway, that's going to be my conclusion of the idea of this proof. What I really want you to get out of it, of course, is the main statements, is that we only need to consider extreme points as potential optimal solutions, which is really what our method is going to do. It's still, of course, possible for an optimal solution of an LP to be not an extreme point. But if that is the case, there must be another optimal solution that is an extreme point. For next time, what I want you to all consider is the fact that last time we saw this. This is the drawing of the polyhedron we saw. In this case, the polyhedron is x1, x2, such that, say, 1 is less than or equal to x1 is less than or equal to 2. And that has no extreme points. So our theorem does not apply to this case. Oh no, well, what are we going to do? What we're going to do is we're going to use a modeling trick to formulate an equivalent linear program that must have an extreme point. And that'll be in lesson 16. Have a great weekend. And don't forget to fill out the Google form that has the lesson test or lesson assessment for 15. That is going to be due by Monday, and I'll issue the exact time it's due on Monday in the form itself. Thanks.